We're starting chapter 11. Chapter 11 is shapes and a lot of formulas involved with the shapes. So we're just going to do basics. 11.1 obviously is just basics about shapes, three-dimensional shapes. Two-dimensional means flat. I could like put it on the desk. A three-dimensional shape is these wonderful things that have depth. So three-dimensional shapes, things like this. We're going to talk about volume, surface area, and all the things that are involved in three-dimensional shapes. So, starting off, little vocab word. I'm pretty confident that you guys all know what these are, but that's okay. An edge is the line where two planes intersect. Where two planes intersect. So two sides of the shape come together, they come together and they make a line. The face is the flat side. So the side of any shape, it could be a triangular side, it could be a rectangle side, a pentagon, a hexagon side, they're all. I could even have a circle side if I was talking about a cylinder. The vertices or the vertex, it's just a point where the edges meet. A point where the edges meet. Okay, how many faces? So what I'm going to do is I'm going to show you how to draw these using, it's called a net. The net is where I flatten out every side and I basically make a little diagram of what the shape is made out of. So this shape has two triangles and three rectangles, right? So I'll have to scroll down. Hope you got the vocab words done. Yeah, that's good. So this has two triangles and then it has three rectangles, right? So that's what the shape is made out of. Triangular prism. This is a triangular prism. This is a rectangular prism. So there's two squares. The top and the bottom are the same size. Two squares. I'll do my best to make it a perfect square. And then four rectangles. So top and bottom are a square, and then four rectangles. So I'll do this times 4. So let's backtrack now and fill in our chart. In a triangular prism, how many faces, flat surfaces, does a triangular prism have? So I'm counting the front, back, left, right, bottom. Front, back, left, right, bottom. Right? So what's that answer? How many faces does it have?
5.
5 faces. My vertices, I can make with a dot. Those are the points. It's a point where they meet. So I just did 6, right? And an edge, I'm going to do in black. So the dotted line means it's behind. 1, 2, 3, 4. That's the bottom shape. 5, 6, 7, the back line, 8, 9 edges, 9 edges. Okay, that's my triangular prism. So my second shape, remember, was a rectangular prism. And my rectangular prism faces, so the 2 squares, top and bottom, and then the 4, front, right, back, left. Okay, so that's going to be 6 faces. Oh, a vertex, a little corner piece. 1, 2, 3, 4, 5, 6, 7, 8. 8 vertices. There's a lot of edges. So I'm just going to trace every edge. You can just watch or do the same on your paper. Bottom square, 1, 2, 3, 4. Top square, 5, 6, 7, 8. Then up and down. 9, 10, 11, 12. Okay. Pentagonal. So the top and the bottom are a pentagon. So I've got 2 pentagons. 1, 2, 3, 4, 5. I'll put times 2. 2 of those. And then all of the other sides, you know, they're not perfectly exactly the same because you can tell how this edge may be longer than like a shorter edge. Anyways, there are 5 rectangles. So on my pentagonal prism, the faces are, basically you're just adding these up, 5 plus 2. So that's nice. A vertex, I'll do my dots again, but I'm sure you can figure this out. If there's 5 at the bottom, there's 5 at the top. So that's 10, right? Then edges. So 5 for each pentagon, 1, 2, 3, 4, 5. 6, 7, 8, 9, 10. And then up and down, 11, 12, 13, 14, and don't forget the one in the back, 15. Okay. This is the weirdest looking hexagon, right, Christian?
Are vertices equal to faces minus 2 times 2?
Well, there's a formula, yeah. We're doing, yeah.
Okay.
Oh, this is the weirdest looking hexagon, right? Because this is super long side, 1, 2, 3, 4, 5, 6. Not a perfect hexagon at all, but my faces. So the hexagon in the front, I'm going to just draw a perfect one, you guys, because I just, oh, that's not going to be perfect. Starting out like that. 1, 2, 3, 4, 5, 6. So there's a basic hexagon, right? There's 2 of them, and then there's 4 rectangles. No, wait, there's not 4 rectangles. Sorry, there's 6 rectangles. These are my faces. So there's 8 faces. My vertices, little dots, 1, 2, 6, and 6, guys, just 6 and 6. Twelve, 6 plus 6 is 12. Yep.
I had a question with edges.
Edges, yep.
Are edges equal to faces minus 2 times 3? That's what the correlation I see with it. Or no?
Faces. What times 3?
If you faces minus 2 times 3.
They all have that pattern, yep.
Well, I was just
So
wondering,
there's
is
this
that with
man.
all of them or no?
Yeah, there is this man. I'm gonna talk, you're like 1 step ahead,
Okay.
just 1 second. Let me finish edges and then I'll tell you exactly what you're talking about, because you're right.
Oh.
The edges are the straight lines created. So 6, 6, 7, 8, 9, 10, hold on, 6, 12, 13, 14, 15, 16, 17, 18. So yeah, you know, as he was saying, there is a pattern to this. Because way back when mathematicians just sat and thought about things, so they were able to come up with these connections. And it's, you know, all of these theorems and all of these rules and formulas that we now know in math was just created by someone in their head, because they're staring at something going, hey, like he was doing in class. Wait, this is a pattern. If I take 2 away and multiply by 3, I get 9. 6 minus 2 is 4 times 3. 7 minus 2 is 5 times 3. Right? So this man, his name is, well, where did I put his name? Anyways, 1 second. So, Leonard, I might be saying it wrong. Anyways, Euler. So he was studying math in the 1740s. You guys want to see a picture? It's not a picture, it's a painting. So, I mean, super handsome dude, right? Hottie. So, super smart. And he's not only popular for geometry, this Euler's law that we're going to talk about right now, there's many, many other things that he's very popular for. So what his theorem says is that it's a little different than what you were noticing, but it's my faces plus my vertices equals my edges plus 2. Faces plus my vertices equals my edges plus 2. And so what you did is you subtracted 2 and you multiplied by 3. So it's a little different, but let me show you how this works. 5 plus 6, my faces plus my vertices equals my edges 9 plus 2, right? And it works for every single one. So I'm going to go through them. 6 rectangular prism, 6 plus 8 equals my edges 12 plus 2. 7 plus 10 equals my 15 plus 2, right? 8 plus 12 equals my 18 plus 2. So that's Euler's formula. The sum of the faces and vertices is 2 more than the number of edges. And you'll notice the edges are always the largest number. In every shape, the edges have the most, right? It's where the two flat surfaces connect. So that's going to happen more often than just a vertex, a point where two lines connect. So I'll scroll down so you can see, well, you can already see it on your page, but for my video purposes, I've got to erase all these numbers. Okay. Now, you're going to be drawing shapes in this chapter. So, as a math teacher, which is so funny, but I would spend a lot of time in elementary school when I was bored and not paying attention to the teacher, for example, drawing shapes. And so you just have to make sure that lines are parallel when you draw a shape. If you're giving it a three-dimensional look, your lines still have to be parallel, but obviously not the same size because I've got to shorten one to bring it straight down, right? So I'm going to make this top line longer. Same thing with my back top edge. Okay. And then the dotted lines in the back are the hardest by far. So the back of the shape, I know that I'm going to have, because it's really easy to like go over and be like, oh, wait, that's too long, right? So I would say parallel lines first. But I'm telling you right now, I need you to practice drawing shapes in the side of your paper. Because I want you to actually have a shape that I can recognize and that you can recognize. Pyramids are hard, boxes are not hard. Box is the easiest thing there is, right? Cylinders are easy. It's two circles and two straight lines, that's easy. Pyramids are difficult. Sphere is easy. Cone is easy. A triangle and a curved bottom, right? So I really do want you guys to sit and practice drawing shapes. And you also need to pay attention to your teachers though. So I'm not telling you to ignore your other teachers. So here it is again. And here's a sample of Euler's formula. Leonhard Euler. All right, I'm gonna go to page 2. Let's practice his formula. The figure below shows a regular hexahedron. It has 6 faces and 8 vertices. How many edges does it have? Well, remember, faces plus vertices equals my edges added 2. Added 2. So, there are 6, it tells me, F is 6, there's 6 faces. There's 8 vertices. And if I don't know how many edges, I would just leave my edges unknown. And obviously I'm just doing simple math. This is like order of operations, right? 14 equals edges plus 2, subtract 2, there are 12 edges. This is one of those things that if you don't really feel like counting and going 1, 2, 3, 4, 5, 6, 7, 8, 9, if you don't want to just count, you would use this formula. And it's great because it works with all 3-dimensional shapes. So it really spans everything. Yeah.
But isn't it inefficient when you can still find the edges with only one variable? Because you can find the number of vertices with faces, or you can even find faces with vertices or edges. So with any of the variables, you can find any of the others. Yeah, if I knew the edges, but I didn't know the vertices, I could sub that in and work that formula out too. Well, no, but I'm saying if you only had one variable, like say if you only knew the amount of faces, you can then find any of the other variables. Well, or like say if you only knew the number of edges, but you didn't know faces or vertices, you could still find faces or vertices. So that's what I'm saying.
You're still
formula kind of inefficient.
Well, he didn't think so. He was in love with his formula, obviously, but There are other ways that may be faster, but at the time that he obviously created it, we're just gonna let him have his glory, right? But yes, there's other ways.
May I use my own?
Yes.
Okay.
Here we go. I'm gonna do game pieces. So these are like dice that are multi-sided. And they're pretty cool. I have this bin of dice that have like 10 sides and 12 sides, and they're just like extremely valuable to me because you just don't find them. You know, it's not like I'm gonna play Monopoly and it's gonna have a 10-sided die. So to make a polyhedron, many sides. Using a 3D printer, one needs to enter the number of faces, edges, vertices into a program, like a computer program. If she wants a game piece with 20 faces, so we're going to use Euler's formula today because that's our important. So it's 20. For faces, I'm going to put 20. For edges, I'm going to fill in 30. And I need to find the vertices. So obviously 20 plus V equals 32. Subtract 20. $12 vertices. And again, this is only used because you don't feel like counting. It's the only time that this is appropriate. Okay, so the relationship between faces and edges and vertices is found using Euler's formula.